Okay, in this lesson, in Unit 3, we're going to work on directed angles and sinusoidal functions. So directed angles refer to, back to our work in angles in standard position. And these are going to include negative angles now, as well as angles that go beyond 360 degrees. So let's review what we know about angles drawn in standard position. The initial side is located on the positive side of the horizontal axis, and the terminal side is a rotation of that initial side. A positive angle represents a counterclockwise rotation. So rather than rotating through quadrants 1, 2, 3, 4 in order, if a negative angle will rotate clockwise and will rotate in the order of 4, 3, 2, 1. A zero angle represents no rotation or a zero rotation. So in example 1, what we're going to look at are some angles that are beyond that normal 0 to 360 range that we've used in the past. So we're going to sketch an angle that measures 420 degrees in standard position. Well, if I start here on the positive x-axis, there's my initial side, and I rotate a total of 360 degrees, that's not going to quite get me where I'm going. So I'm going to rotate 360 plus an extra 60, and that would bring me to 420 degrees. So that spiral that you see right there represents 420 degrees. What we want to sketch in the grid below it, or the coordinate plane below it, is an angle that has an initial side in the same place on the positive x-axis, a terminal side in the same exact place, but is now an angle that's between 0 and 360 degrees. So if it's a positive angle, then that would have to be 60 degrees gets us to the exact same place. So 60 degrees is an angle that ends up in the same place as the terminal side of a 420 degree angle. All right, let's take a look at B. B is a negative angle. So we're still going to start here on the positive x-axis, because that's where all angles start, or that's where a 0 degree rotation is. Now we're going to rotate negative 135. That means we're going to go in a clockwise direction. And if we rotate 90 plus an additional 45 in that direction, that'll put us smack dab right in the middle of quadrant 3. So that's a negative 135 degree rotation. And notice I put an arrow on there to indicate the direction of rotation. Now what we want to do is create an angle that has the exact same initial side and terminal side, but we want a positive rotation that's between 0 and 360 degrees, and you're going to recognize that one as 225 degrees because, remember, in order to rotate into quadrant 3 above, we had to rotate a 90 plus an additional 45 degrees, and that means that we're 45 degrees into quadrant 3. So if we go in a positive direction, we're going to go 180 degrees, and plus an extra 45. So 180 plus an extra 45 is 225. All right, let's check out one more. And then this one is a negative 450 degree angle. So that means that I'm going to start again on the same place that we always start, which is the positive x-axis. And we're going to rotate in a clockwise direction since it's a negative angle. That's going to give me 360 if I do one full rotation. And so I'm going to want to go an extra 90, and that would be a negative 450 degree rotation. So that puts our terminal side here right on the negative y-axis. Now what we want to do is create an initial side and terminal side that are the exact same as that angle above, but create an angle that's positive between 0 and 360 degrees that gets us to the same place, and you'll recognize that one as 270. All right, let's pause the video and then try D on your own. Here's the solution to D. For a negative 240 degree angle, you should have rotated into quadrant 2, but in a negative direction, and then a positive angle between 0 and 360 that ends up in the same place or has the same terminal side is a 120 degree angle. That brings us to a definition. What we've been talking about, but we haven't said exactly, is angles that share a terminal side are called coterminal angles. They terminate in the same place. A coterminal angle can actually be found by adding or subtracting one or more full rotations, because a full rotation gets us back to where we started, or that is, adding or subtracting any multiple of 360 degrees. So, in example 2, we are asked just to find coterminal angles to the given angle that lie somewhere between 0 and 360 degrees. So we're going to subtract off full rotations from 800, and if we subtract off 360 from 800, we're not quite going to be small enough to be in between 0 and 360. Notice that it's possible to subtract off 2 full rotations from 800 and have the resulting angle still be a positive angle. So 800 minus 720 degrees gives us an 80 degree coterminal angle. In B, we have a negative angle. In order to create a positive angle from this, we'll have to add multiples of 360 degrees. Well, let's list some multiples of 360. We've got 360, 2 times it is 720, 3 times it is 1080, and 4 times it is 1440. It looks like it's going to take adding 1440 to the negative 1300 in order to get an angle that's positive in between 0 and 360. So a 140 degree angle is coterminal. Pause the video and try C on your own. All right, here's the answer for C. You should have gotten a 20 degree coterminal angle by adding 2 full rotations, or 720 degrees to the angle. All right, moving on. Since coterminal angles actually share a coterminal side, they also share a reference triangle, and therefore their trigonometric ratios are equal. So if I take the sine of 2 coterminal angles, I'm going to get the same exact result. All right, so in A, we're going to evaluate the sine, cosine, and tangent of each angle. So sine of 660, cosine of 660, and tangent of 660. Let's see if we can sketch a reference triangle. So 660 minus 360, a full rotation, gives us a 300 degree angle. That's the angle that we want to sketch. So sketching a 300 degree angle, that's going to be a quadrant 4 angle that'll terminate in quadrant 4. That's just a little bit beyond 270, right? So if I have an angle that terminates in quadrant 4, our reference angle is 60 degrees, because 300 plus 60 degrees is 360, or a full rotation. And we know that our opposite to the 60 degree angle is square root of 3, the small side is 1, and hypotenuse is 2 for a 30, 60, 90 triangle. But wait, we need to be cognizant of the side that is hanging down there. That's going to be a negative side. So we'll treat our opposite side as negative. So sine is opposite over hypotenuse, negative square root of 3 over 2. Cosine is positive 1/2, that's adjacent over hypotenuse. And tangent is negative square root of 3 over 1, opposite over adjacent. And that's going to simplify to negative square root of 3. We always want to simplify if we have an expression that's divided by 1. There's all of our answers. Try B on your very own, so pause the video. Okay, you should have found a coterminal angle of 135 degrees and then sketched a reference triangle with a 45-degree reference angle, and that gives us sine of negative 225 is positive 1 over root 2, which rationalizes to square root of 2 over 2. Cosine would be negative 1 over root 2, which rationalizes again, and tangent is 1 over negative 1, which simplifies to negative 1. Now, in this unit, we're also going to be working with parent functions. And the parent functions are developed from this idea that we just talked about, coterminal angles and cyclical behavior. So each of the 3 functions that we talk about in this unit is what we call a periodic function. That's a function that repeats its value at regular intervals. And so sine, cosine, and tangent all turn out to be periodic functions. All right, if I want to get some values here to plot, if I want to plot y equals sine of theta, I'm just going to create a table of values, and we're going to plug in some theta values here and find out the y values. So this first value here, if I plug in 0 degrees, it's asking me to find sine of 0 degrees. So let's refer to a circle. We should have here somewhere. There we go. Let's refer to this circle, and if we're at 0 degrees, that's going to be a side an angle that terminates right there. Let's remember what our coordinates are at 0 degrees. That would be 1, 0, since the horizontal is 1 and the vertical coordinate is 0. Remember, that's our A and our B, right? A is the horizontal side, which is the adjacent. B is the vertical side, which is the opposite. And if we use the Pythagorean theorem, that's going to give us a C value of 1. So that means that sine of 0 degrees is equal to the opposite over the hypotenuse, and 0 over 1 is equal to 0. So we can put that value in the table. Okay, now let's look at 30 degrees. 30 degrees, we can go back to our angle template here, and we can sketch a 30-degree angle. You don't really need a circle to sketch this, but you can utilize one if you wish. You just really need to draw a triangle. And we have a 30-degree angle, and that means that opposite is 1, adjacent is square root of 3, and the hypotenuse is 2. So that means sine of 30 degrees is 1/2. And I'm just going to write that in decimal form as 0.5. All right, now let's check out 60 degrees. Well, I think you can see from 30, 60, 90 triangles, which we've drawn a lot of, that the sine of 60 degrees is just going to be square root of 3 over 2, because in that triangle, our opposite and adjacent just switch sides. So we'll have square root of 3 over 2. And let's get a decimal approximation on that one, because what we're going to need to do with this is plot it. So we're going to grab our calculator here and just type in the square root of 3 over 2. If you type that in, you have to be very careful to use your cursor and get out of the square root before you write the division. And that's about 0.87. I don't think I can graph it to 3 decimal places, so I'm just going to write 0.87 there. All right, sine of 90. That's back to our template here. 90 degrees is up here at this point, and that's going to be coordinates of 0, 1. So now our vertical coordinate is 1, and our hypotenuse is 1. So sine of 90 degrees is the opposite, which is the vertical over the hypotenuse, which is going to equal 1. All right, promise this is going to go faster in just a moment. What happens when we move into Quadrant 2? Well, our sine values are going to actually go back down, and they're still going to be positive. So sine of 120 degrees is the square root of 3 over 2, or about 0.87. Sine of 150 is a half, or about 0.5. Sine of 180 is back down to 0. As we rotate through the rest of the quadrants, going into Quadrant 3, the sign goes negative. So our next value at 210 is negative a half. At 240, negative 0.87. At 270, the sine value is at its most negative, negative 1. Then 300, we're going back toward 0. Negative 0.87, negative 0.5, and 0. All right, let's plot some points now. You'll notice that on the horizontal axis for theta, we have 30-degree increments, and on the vertical axis, we have tenths marked off so that we can graph these fairly accurately. So we have the point 0 degrees, y is 0. So that's 0, 0. The next point is 30 degrees, a half. The next point is 60 degrees, 0.87. So that's up there, not quite to 0.9. 90 degrees, 1. 120 degrees, 0.87. 150, 0.5. 180, 0. 210, negative a half. 240, negative 0.87. 270, negative 0.1, or negative 1 actually. 300 degrees, negative 0.87. 330, negative a half. 360, 0. So that's all we have for our table. Let's actually connect those points together. I'm just going to use a different color so we can see our points fairly accurately as well. So if we connect those with a nice smooth curve, I think we can agree this is not a straight line. Now, knowing what we talked about before, if we go to 390 degrees, the value of sine is the same as it is at 30 degrees. This just repeats itself. It's a coterminal angle. And then we can actually just fill in the rest of the cycle because it's going to repeat itself. This is the second rotation through that circle. So I'm just going to fill in the rest of these points here until we get to the end of the grid. Once we have all those points, then we can continue the graph. Now there's more to this grid that we can certainly fill up. We can go back in the other direction and graph another cycle. And it's the exact same pattern that happens over and over again. Let's connect that with a nice smooth curve. And what we can see here is this, we've shown 3 full cycles of this graph. I'm going to highlight this part right here. and this part we could actually say is the principal cycle, or the part that's in between 0 and 360 degrees. All right, so this is what the sine function looks like with a lot of points plotted for accuracy, so we can get an idea of how curvy this is. In practice, when you graph this, you're not going to graph as many points. It'll be much easier to plot. But I want you to get a feel for what it looks like. All right, let's take a look at the cosine function now. And let's go back to our circular template here. And we have cosine of 0 is the very first thing that we want to explore. So cosine of 0, we're going to utilize this point right here at 0 degrees with coordinates 1, 0. The cosine of 0 degrees is the adjacent over the hypotenuse, which is going to be 1. Now think about what's going to happen as we go in this direction to 30 degrees and to 60 degrees. Our adjacent side is doing what? Shrinking, right? And so that means the cosine is going to shrink from this point forward. That's going to allow us to put some of these values in a little bit more quickly. All right, so cosine of 0 degrees is 1. Whoops, that would be the wrong pen. Is 1. Cosine of 30 degrees is the square root of 3 over 2, which is, we said, about 0.87. Cosine of 60 degrees is a half, which is exactly 0.5. Cosine of 90 degrees is 0. When we go into quadrant 2 angles, cosine becomes negative. So now negative 0.5, negative 0.87. Cosine of 180 degrees is negative 1. Past that, cosine continues to be negative, but it shrinks in size. So negative 0.87, negative 0.5, and then 0 at 270 again. And then once we're into quadrant 4, beyond 270, that's 0.5, 0.87, and back to 1. All right, let's plot those points. So 0, 1, 30, 0.87, 60, 0.5, 90, 0, 120, negative 0.5, 150, negative 0.87, 180, negative 1, 210, negative 0.87, 240, negative 0.5, 270, 0, 300, positive 0.5, 330, positive 0.87, and 360, 1. Here is one cycle of the cosine function. And that's, again, this part we can say is the principal cycle, the part that's just between 0 and 360. So let's kind of color that in here to highlight that fact that that's one full cycle of the graph. And then we can continue beyond 360 and also in a negative direction and just repeat that same cycle again. So let's just plot some more points to get a nice accurate graph for the rest of this repeat cycle here. Now that I'm looking at this, I realize I made a little boo-boo there on the first cycle. See that point at 180, negative 1 should have been at 180, negative 1. Not where I plotted it. I think I plotted it at 0.9, so it should have dipped just a little bit more there. Sorry about that. And let's finish the rest of the repeat cycle. So it's just repeating these same exact values over again. Let's scroll over just a little bit so that we can plot the rest of those points. And sketch in the rest of the cycle. Now we can do the same thing in the negative direction. The same repeat of those same values over and over again. And once you're finished with all those points, just connect for a nice smooth curve. Whoops, that wasn't a great one on my part. All right, let's back it up and look at the whole thing. You can see those 3 cycles and maybe just a little bit more there. So that is the cosine function. All right, now let's take a look at the tangent function. So for the tangent function, let's go back to our circular template here. And in the tangent function, for 0 degrees, we are at that point on the positive x-axis. So again, right here, for 0 degrees, we have the point 1, 0, and tangent of theta is or tangent of 0 degrees actually, is the opposite, the vertical coordinate, over the adjacent, the horizontal coordinate. So tangent of 0 degrees is 0. Now let's do tangent of 30 degrees. Back to that circular template. And we'll sketch a 30-degree reference triangle. Tangent is the opposite over the adjacent. So tangent of 30 degrees is equal to 1 over root 3. Now I don't care if that's rationalized because we're really going to have to get a decimal value to plot it. So let's refer to our calculator here. 1 over root 3, you can do that with control divide if you want. That makes it a little bit easier. 1 over root 3. Said it was easier. All right, there we go, is about 0.58. Tangent of 60 degrees. Let's go back to our circular template. Tangent of 60 degrees. That's not 60 degrees. That looks better. So tangent of 60 degrees is opposite over adjacent, which is the square root of 3 over 1, or just the square root of 3. Let's find out what the decimal value of that is. So we want the square root of 3 is about 1.73. And then at 90 degrees, let's check out 90 degrees. That would be up here at the point 0, 1. And tangent of 90 degrees would be the opposite, the vertical coordinate, over the adjacent, which would be 0. That's the horizontal coordinate. And that's going to be undefined. So I'm going to write that in my table here, that the tangent of 90 is undefined. We'll just abbreviate undef. All right, and then in quadrant 2, what we know about 120 degrees is that it shares a 60-degree reference angle, so it's going to have the same sort of value or same triangle that the 60-degree angle has. But in quadrant 2, tangent is negative. So we'll have a negative 1.73 At 150 degrees, the tangent is about negative 0.58. At 180 degrees to 0. When we cross over into quadrant 4 angles beyond 180, the tangent in quadrant 3 becomes positive. So 0.58, 1.73, undefined, and then negative again, 1.73, 0.58, negative 0.58 that is, and at 360, 0. So let's plot that. We have 0, 0, 30 degrees, 0.58, so not quite 0.6, 60 degrees, 1.73. It's going to be way up there. And then 90 degrees, undefined. I think you've seen this before in some graphs where if there's a 0 in the denominator, we have a vertical asymptote. So I'm going to draw in a little dashed line for a vertical asymptote there at 90 degrees, and I'm just going to go ahead and do it at 270 degrees, another place where we have an undefined value for tangent. And then we can repeat that cycle later when we sketch the rest of this. So this piece of the tangent function looks like it's shooting up toward infinity. Now let's graph the next piece, 120 degrees, comma, negative 1.73. So adjusting, sorry about that, and then negative 1.73. That's going to be way almost down to the bottom of the graph here. And next angle is 150 degrees, negative 0.58, 180, 0, 210, 0.58, 240, 1.73. Nice little shape there. Curvy, but looking kind of vertical there. And then at beyond 270 at 300, we have a negative 1.73 tangent value. At 330, a negative 0.58 value. At 360, 0. So there's the 0 to 360 degree range. But what you'll notice is this is repeating a lot more often. Let's sketch in the rest beyond 360 here. So we're just going to repeat the same pattern again. There's the rest of that piece, followed by a vertical asymptote at 450. And then we can sketch a little bit more. And maybe we won't sketch in all of the cycles. We have a vertical asymptote there at 630, because this one repeats a little bit more often. Let's sketch it in the negative direction, though. So at negative 30, we'll have a value of a negative 0.58. And at negative 60, we'll have a value of negative 1.73. And then we'll have another vertical asymptote there at negative 90. So it looks to me like we could say one primary cycle of this graph is between negative 90 and positive 90 degrees, which means this one repeats every 180 degrees, not like the sine and cosine, which repeat every 360 degrees. In the last part of this lesson, we're going to look at a couple of terms that we need to be familiar with. The first is the period of a function is the horizontal length of one cycle of that function. So in example 5, we see what's called a periodic function. That is, you see it repeating the same cycle over and over again. And we can measure where one cycle begins and the next one ends. So, for instance, one whole cycle could be this graph going downward and then back upward to the same peak. So if I treat that as one full cycle, then we need to find the horizontal length of that one cycle. I'm going to make this look a little bit bigger here, and it looks like this cycle starts at about 3.5 and it ends at about 9.5. So the length of the cycle then is 6. You can do this in some other ways, marking off some other points here. If you wanted to start your cycle right here in the middle and then travel through the cycle this way, that would have us starting here at -4 and ending at 2, which is still a cycle length of 6. So what we're going to say on this one is the period is equal to 6. All right, let's take a look at B. In B, we have another cyclical function. Maybe the easiest way to look at the length of one cycle is either to look from a lowest point to a lowest point, or a highest point to a highest point. You can take your pick. This lowest point occurs at x equals -1 and the highest at +7. There's a distance of 8 units in between those, so the period of this function is 8. This next one looks kind of like that tangent graph that we just looked at. It's got a series of asymptotes. I think we can measure one cycle as the portion between two asymptotes. So here at -4 all the way to 1, that's going to give us a cycle length of 5. So the period of this function is 5. And let's take a look at the last one. This one's a lot slower of a cycle. If we go from this max point to another max point right here, that looks like that happens at -11. And this next one happens at +5. So the distance between -11 and +5 on the x-axis is 16. So the period of this function, it's a little slower function, is 16. The graphs of sine and cosine are actually examples of periodic functions, but also what we call sinusoidal functions. That is, they have a specific curvy shape that just goes up and down, like a wave. In fact, sines and cosines are used to model wave motion. The amplitude of a sinusoidal function is the vertical height of the graph above its mean y value. So there's a couple of different ways that you can calculate this. You can figure out where that middle value is, the middle y value. That would be, seems to be right there on this function. And then, let's zoom in a little bit more on this one. The amplitude is this vertical distance above the middle y value. So the amplitude is that distance there from 1 all the way up to 5. So it looks like the amplitude of this sinusoidal function is 4. Another way to find this is also to just take the high value and the low value and subtract them. So our high value is 5 and our low value is -3. So that's a distance of 8 in between those two values, and then just half of that is the amplitude, because the amplitude measures the distance from the middle value up to the maximum. All right, let's take a look at B. In B, we can figure out where that middle value is, right through the middle of the function. The amplitude is that distance above. So it looks like our amplitude on this function is 2. In C, if you can find that middle value, that's probably the easiest way to do this, and then the distance above it. So that's from 1 to 6 is 5, so our amplitude is 5. Another way to find it again is max value is 6, the min value is -4. There's a distance of 10 in between that, half the amplitude, half of that value, 10 is 5, that's the amplitude. And last one for D, here's our middle value. The amplitude is the distance the wave goes above that. So our amplitude here is 3. All right, and that's it for this lesson.